Hey, this is Horner, and this is our last video for what you need to know in order to get a passing score. Rotational motion. So this part is on rotational kinetic energy. We've been through all the other parts, and this is logically the last one. So when we first did kinetic energy, we thought about things traveling in a straight line. So if I have a truck traveling in a straight line and I know its mass and its speed, I can find its kinetic energy. But if I want to find, let's say one of the tires comes off the truck, and I want to find out what its energy is, its kinetic energy, it has both this type of energy, energy in a straight line, and it has rotational energy. So the energy due to it rotating in that circle. So it has energy, kinetic energy in this direction as it moves from left to right, and it also has kinetic energy in the motion of the circle. So we can actually add both of those together. When we've had an incline and we had the ball rolling down an incline, it actually loses a little bit of energy due to its rotational motion. So when we said it was going a certain speed here, it really wasn't. It was actually going a little bit less because some of that kinetic energy is tied up in the actual rotation of the ball itself. So let's go through and try to do some of these. The first one says Gina rolls a bowling ball, mass 7 kilograms, and a radius of 10.9 centimeters down a lane with a velocity of 6 meters per second. So that's linear velocity. They want us to find the rotational kinetic energy of the ball, assuming that it doesn't slip. So we know that there's got to be some friction so it doesn't slide down the lane. The moment of inertia for a bowling ball is of a solid sphere, so that's 2/5 mr squared. So we're going to do 2 over 5 times the mass, which is 7, times the radius, and we've got to be careful, this is in centimeters. We're going to put it in meters, 0.109 meters, and we're going to square it. And you should end up with 0.0333 kilograms times a meter squared. The next thing we need to do is find the ball's angular velocity. So remember that's omega, and omega is equal to v over r, because remember the linear is always equal to the angular times the radius. So this is equal to 6 meters per second. That was our linear, that was our linear speed, and we need to divide it by the radius, which was 0.109. And so we end up with 55, and remember this is measured in radians per second. So our kinetic energy that is rotational is equal to 1/2 of I, which is the moment of inertia, which is kind of like mass, times the angular speed, which is like linear speed, squared. So this is equal to 1/2 of 0.0333 times 55 radians per second squared. If you do that work, you'll end up with 50.4, and just like any other energy, the unit is a joule. The next thing they'd like for us to do is find the total kinetic energy of the bowling ball. So it's got to be the kinetic energy from both the rotation and from it just moving in a straight line. So this ball, when she pushes it, is moving in this direction. It's also rotating. And so we have to take the kinetic energy that's linear and add it to the kinetic energy that's rotational. So here we go. We're going to do kinetic energy is equal to 1/2 mv squared plus 1/2 I omega squared, where this is the straight line and this is the rotating. We already know what this is. We said it was 50.4, so we just have to find out what is the linear. So that's 1/2 of 7 times 6 squared plus, and then we had 50.4 joules. If you do your math here and add it to the 50.4, you'll find out the ball actually has 176 joules of kinetic energy, which is quite a bit. And that's how you do number 38. Let's go ahead and move on down. The next problem that we have here is involves Harrison. So Harrison is kicking a soccer ball, which rolls across the field. It does not slip, and it's moving at 5 meters per second. They want to know what is the ball's kinetic energy. We're going to treat it as a hollow sphere with a mass of 0.43 kilograms and a radius of 0.11 meters. First thing we need to do is find out what is the moment of inertia, and we know for this ball it is 2/3 times the mass times the radius squared. So this is 2/3 of 0.43 times 0.11 squared, and so we end up with 0.00347 kilograms times a meter squared. Next thing we need to do is find the angular speed here. It's v over r. Its regular speed, linear speed is 5, radius is 0.11, and so that ends up being 45.5 radians per second. So our total kinetic energy is 1 half mv squared, that's the linear, plus 1 half I omega squared, that's the rotational. So this is equal to 1 half of the mass, which is 0.43, times the velocity, 5 squared, plus 1 half of 0.00347 times 45.5 squared. So that's I times omega squared. If you do all that math, you should get 8.96 joules of kinetic energy. Next problem says an ice skater spins with a specific angular velocity. She brings her arms and legs closer to her body, reducing her moment of inertia to half its original value. What happens to her angular velocity? So for this one, this is more of a thinking, reasoning question. And I can tell you that as the skater pulls her arms and legs in, she reduces her moment of inertia. So her moment of inertia decreases. Since there's no external net torque, her spin angular momentum remains constant. So her original angular momentum is equal to her final angular momentum. But her rotational kinetic energy, on the other hand, because the I gets smaller, remember rotational is 1 half I omega squared. Because this is cut in half, her angular velocity has to double. Therefore, her rotational kinetic energy is doubled. So her kinetic rotational energy is doubled. The skater does work when they pull their arms and legs in, so that gives it more energy. So even though we half this, her angular velocity has to double. When it doubles, then we see that her rotational kinetic energy also doubles. So that is number 40. For the very last one that we have, this is kind of a fun one. We have a ball on a hill. It's actually a disc, so it's like a frisbee. And it has a radius r, and it's rolling down this hill without slipping. And the height of the incline is delta y here. I know that it says that it's h, but it's really delta y. Let's get rid of that. Delta y. There we go. They want us to find the speed at the very bottom. So they want to know what is the speed of this thing at the very bottom. Notice they don't give us any numbers, so we actually want to do this using just letters. So we know that we're conserving energy. So our original kinetic energy plus our original potential energy should be equal to the final kinetic plus the final potential. If at the top it doesn't have any speed, we know the kinetic energy at the top is 0. And at the bottom it doesn't have any height, so this final potential energy is 0. Let's go ahead and write our equation again. So this is the original potential energy. And by final kinetic, remember we have two types. We have kinetic energy that is linear plus kinetic energy that is rotational. So let's go ahead and put equations in for these. Remember, the potential energy due to gravity is just mgh. So we actually probably could put mu og here. And this is really potential energy due to gravity. There we go. That's equal to mg times the change in height. So let's actually put in the change in y, since that's what we have here. And that's equal to 1 half of mv squared plus 1 half I omega squared. We can go ahead and put these in again. mg delta y is equal to 1 half mv squared plus, here we go, we're going to do plus here. And then for this disk, the rotational inertia around the center of the mass, that's all that means, of the disk is 1 half. So here we're going to do 1 half mr squared. And then we multiply that times our omega squared. Now that we've done that, we see that we can combine these two. So we have mg delta y is equal to 1 half mv squared plus 1/4 mr squared times omega squared. But remember, the velocity is equal to omega times r. So what I can do is I can plug in For this omega, omega is equal to V over R. I can plug this in at this point, so that's what I'm going to do is I'm going to take the V over R and stick it in here, but notice I have to square it. And while I do that, I'm also going to get rid of my M's. Notice that there are M's all the way across. We can get rid of those. So this is now G times the change in height is equal to 1/2 of the velocity squared plus 1/4. Now I'm going to have R squared times omega squared, but that's really R squared times, and then this thing becomes V squared over R squared. So notice your R squareds now cross off, and we have 1/4 the velocity squared. Now we can add these two together, and if I do that, I'm going to make this, instead of 1/2, this is going to be 2 over 4. So 2 over 4 plus 1 over 4 is 3 over 4, so this is G times the change in Y is equal to 3/4 of the velocity squared, and they want us to solve for this velocity. So now our velocity is equal to 4 over 3, so our velocity squared is 4 over 3 times G times the change in Y, and then if I want velocity, I have to take the square root of both sides. So now I get velocity is equal to the square root of 4 over 3 times gravity times the change in my height. And that will be the speed of the ball when it gets down to the bottom. The very last slide that we have here basically just goes through and gives you a good summary of everything that we've done. Shows you how all of these things are related. That if I want the translational or the linear, I just multiply whatever the angular is times the radius, and you see that all the way down. The only thing it doesn't work for is time. And then force and torque are related by this equation, which inherently has the R in it. So that is the end of the lectures for, or in the video notes, for rotational motion.